Hello, y'all. Welcome to lesson 58 of my DP chemistry curriculum. Today we're starting structure 2.4, doing 2.4.1. We're going to be talking about bonding as best described as a continuum between ionic, covalent, and metallic models and can be represented by a bonding triangle. We're going to use the models to explain the properties of a material. So before we really go into this section, let's kind of talk about what it's about. We're looking at mostly materials. This is where we get into the aspect of material science or materials chemistry. How do people select the proper combination of elements or the proper substance for a job? So as we do that, we're going to be looking at their properties and with their properties, how they're influenced by the bonding models that make up the material. So with that said, let's talk about the continuum of bonding. So we have three types of chemical bonding that we have discussed over the past few lessons. So the first one is ionic. So with ionic, the main focus is that ionic is between oppositely charged ions. Oppositely charged ions. And remember, all of these chemical bondings are just different forms of um, electrostatic interactions. And what we're doing is we're focusing on the different charged particles that take place in the bonding. So we have ionic, which is between oppositely charged ions, so full ions. We have covalent, which is between our shared pairs of electrons, shared pairs of electrons, and the positive nuclei of the atoms in the bond. So instead of having two different ions, we now have electrons in a nucleus. And one of the big things about covalent is it's directional. Lastly, we have our metallic. Metallic is a lot more abstract, and that is specifically between the lattice of cations and delocalized electrons. So they're all the same thing, of positive negatives interacting, but how we look at them and how these particles interact and which particles interact is what changes between them. And so when we think of these bondings, we think of them as three separate things. So if we created a triangle where our 3 points are our three types of bonding, we could put ionic at the top. And just a moment here. Be nice to kind of have an isosceles triangle. We have ionic, covalent, and metallic. Now, when we look at these bondings, ionic is those oppositely charged particles, positive, negative, positive, negative, positive, negative. And this is usually metal plus nonmetal. Our metallic is those positive cations in a lattice with our negative electrons floating around, having those electrostatic interactions with each cation they're close to. And lastly, covalent is those shared pairs of electrons between two positive nuclei. We can look at water, we can look at benzene, which we talked about, and this is going to be nonmetal plus nonmetal, while metallic is metal plus metal. So you'll notice as we go from left to right, we move from metals to nonmetals, with ionic being the combination of the two. So even here, we see a little bit of a continuum, or it's kind of a little more of a loop like that. So it's the shift, which means these bonds must have a bunch of things in common. And we use a triangle because it kind of shows that continuum. So let's take an example. Let's look at the right side of this pyramid right here. So we'll replicate that down here. So what we want to take away is bonding is a continuum. And so let's take it away with the right side. At the top, we have our ionic bonds. And at the bottom, we have covalent. Now, we have different kinds of covalent bonds. If we take some examples, like let's say chlorine bonded to a chlorine, this is going to be a non-polar covalent. But if we replace one of those chlorines with a hydrogen, then suddenly we have a polar covalent. You'll notice in the polar covalent, we start forming partial charges. So they're not full charges, but they're getting there. And lastly, we replace that hydrogen now with a sodium. And now we just have a straight up ionic bond, which with actual full-fledged charges, we have our positive and our negative. So even this is a continuum. And within here, we have different examples where instead of hydrogen and chlorine, we could have hydrogen and bromine, or hydrogen iodine, or above, we could have hydrogen and fluorine. We can go different ways about this. We can have somewhere in a slightly less ionic territory, but somewhere in between polar covalent, uh, boron and fluorine, or even as we've seen, beryllium and fluorine can make what we consider covalent bonds. So we've already noticed exceptions happening, which kind of show this continuum or change towards an ionic character. So this would be an increase in ionic character. Now, within your data booklet, you actually do have this bonding triangle much more fleshed out and divided between ionic and covalent characters, as well as you'll actually have axes to determine where any bond is. We'll be going over that in our next section. What we want to focus on here is mostly the idea of materials. How do we do this? How do we figure out materials from character and properties as well? And the main thing is that properties are pretty much dependent on the bonding, on the bonding. We've seen that before already where like ionic compounds are brittle while metallic compounds are malleable. And covalent compounds, depending on whether they're giant covalent or regular covalent, can be anywhere in between. Which means because it's dependent on the bonding, the different properties are also on a continuum, on a parallel continuum, basically. So we can always refer one to the other. A couple properties we have not explored that still exist here is new ones are like flexibility, which is able to deform and reform back. You can think of a piece of plastic that you can bend and bend right back. And it's very similar to malleability, but it's based in different types of bonding. Similar to malleability. All right. And then the other one is insulating, which is just the opposite of conductivity. So if something's conductive, it's not insulative. And if something is insulative, it's not conductive. And this actually counts for both thermal and electrical. So we can have both thermal and electrical insulators. So one of the things that we want to leave off on before we close out this very short unit in this very short video is that when a scientist is trying to make something new, they want to make a new like pen tip maybe. They want something that's going to be hard, something that's going to be easy to manufacture, but it also can't be too hard. It has to be soft enough to not break paper. It has to be non-corrosive to ink. It has to be not soluble. because ink is usually water-based and you don't want your pen tips dissolving. And so we look at all these properties and we try and find something in our triangle where it will fit, and it'll probably be something metallic. But then if we're looking at the pen, the actual pen minus the tip, we're probably going to go with the plastic. And so what you need to understand is that all the properties come together to help us figure out what kind of bonding we're going to be looking for, which help us decide what material we're going to be using, metallic, ionic, covalent, or somewhere in this in between area. So I hope this gives you a little bit of an introduction into materials and how they relate to bonding and their properties. So have a great day.